Welcome to the third walkthrough, Lab 3, the power of good sampling for simulating a chemistry Hamiltonian with SQD, part of the Qiskit Global Summer School Lab series. My name is Yuri Kobayashi from IBM Quantum, and in this lab, we explore one of the most promising applications of quantum computing, which is quantum chemistry. We present you with a real-life example of simulating a molecule using a quantum computer based on a workflow that quantum chemists may usually follow. As you can tell from the table of contents, this lab is divided into 5 parts with 5 exercises and a bonus exercise in the end. Part 1 to Part 2 provides the background knowledge necessary to tackle the exercises in this lab. If you're already familiar with computational chemistry, I recommend that you skip reading the text in this section and go straight to solving exercise 1 and then quickly move on to part 3. As always, before you begin, please make sure you have installed the latest version of Qiskit, runtime, add-ons, and ecosystem package, and have imported necessary libraries. So in part 1, we begin talking about atoms and their electronic structures, which is a study about how electrons physically arrange themselves in atoms and molecules. To calculate interesting properties of molecules, we usually need to solve for the wave function that satisfies the Schrödinger equation. But we quickly learn that solving the Schrödinger equation is not easy. And therefore, we need to rely on certain approximation techniques, such as using basis sets to simulate the molecular orbitals that make up our Hamiltonian of interest. Here you will get to learn a few common basis sets and then get a sense of how large your molecular Hamiltonian may grow, depending on how accurately you want to simulate your molecule through some examples and then an exercise. So in the first exercise, you will get to calculate the size of an oxygen molecule in a specific basis set. You'll be given all the necessary detail numbers to do this calculation. And if you just follow the example prior to this exercise, solving this will be pretty straightforward. In part 2, we briefly review a well-known quantum classical hybrid algorithm, variational quantum eigensolver. Now, VQE has been one of those algorithms computational chemists have explored on near-term noisy quantum systems for the past decade or so. However, the iterative computational steps for executing VQE, as you see in this diagram, is a costly procedure and can become a limitation to scale to work with larger molecules, which leads to the motivation for us to learn about this new algorithm called sample-based quantum diagonalization. Part 3 gives you a general idea behind the SQD algorithm and why it is useful. And what better way is there to learn about SQD than to look at an actual example? So, Part 4 demonstrates how to use SQD to find an approximation to the ground state of a nitrogen molecule at equilibrium in the 631G basis set. This is what the molecular Hamiltonian looks like. And the basis set approximation you learned at the beginning of this lab is used to calculate molecular integrals shown in both the first body term and the second body term of our Hamiltonian, and will be computed using PySCF. Now, SQD requires a quantum circuit ansatz to draw samples from. An ansatz is the initial guess of the quantum state that represents our molecular Hamiltonian, and in this lab, we use an ansatz called local unitary cluster JASTRO, LUCJ. The reason why we choose this ansatz is because it's designed nicely, sort of combines physical intuition based on the chemistry of the molecule and also hardware friendliness. In other words, LUCJ ansatz takes a form that effectively maps the initial state to our quantum hardware in a way that minimizes costly swap gates, while also respecting the physical intuition that comes from the electronic structure and electron correlations of the molecule. So if you take a look at IBM quantum hardware, you will notice that it has this heavy hex lattice topology. In building your quantum circuit based on LUCJ, the orbitals with the same spin are mapped to qubits with a line topology that adopts this zigzag pattern. The red circles represent the alpha spin particles, which are the upspin electrons, and the blue circles represent the beta spin particles, which are the downspin electrons. And the connection between these orbitals of opposite spin is represented by these purple circles and is present at every fourth spatial orbital. Now, it is important to choose the best physical qubit layout when building your quantum circuit. And later on in this lab, you will be given an exercise to demonstrate just that. So now let's look into the actual SQD workflow. SQD is a post-processing technique, and it involves a self-consistent configuration recovery procedure. Here on the left, we have our LUCJ ansatz circuit to generate many samples of possible electron configurations. We take the generated samples, apply a probabilistic procedure to correct noisy samples, and then we randomly subsample from those good samples to form a subspace to project a Hamiltonian that will be much smaller than the original Hamiltonian. This will allow us to diagonalize the Hamiltonian matrix much easily to obtain the lowest eigenvalue and eigenstate corresponding to the lowest energy state. Here on in this lab, you will learn in detail how the configuration recovery process folds out, and then you will get to combine everything together to implement each step following the so-called Qiskit patterns. Now, Qiskit patterns is a general framework for breaking down domain-specific problems and implementing them in stages based on required capabilities. In step 1, you map your problem to the quantum circuit. In step 2, you optimize that circuit based on the target quantum hardware. And then in step 3, you execute that circuit on the target quantum hardware. And step 4, this is the last step, you do the post-processing where we run our SQD algorithm. After a number of iterations of the configuration recovery step, you will be able to plot your energy estimations and average occupancy of spin particles in each spatial orbital. In exercise 2, we ask you to try applying configuration recovery yourself. Now, for working on this exercise, I strongly encourage you to go to IBM Quantum Learning and then to the Quantum Diagonalization Algorithm course to section and refer to section 4.1, where they describe in detail the logic behind how bit strings get corrected. Now moving on to part 5, which is the last part of this lab. Here you will be given 3 final exercises. So while SQD algorithm is very powerful, it is still ansatz sensitive. So there's still room to improve our ansatz that could help give us better energy calculation results. So here in part 5 and the exercise 3, we ask you to first try a different basis set, a one that can more accurately approximate the molecular integrals of the nitrogen molecule. And next, in exercise 4, we ask you to figure out the best qubit layout for a quantum circuit based on a specific IBM quantum backend. And lastly, in exercise 5, we ask you to try adding additional interactions to the operator you apply to the reference data in the LUCJ ansatz. Here, instead of limiting interactions to the nearest neighbor spins, you will include an additional adjacent spin to create a model that is a little more closer to the actual electronic model in nature. Now, although this is the last exercise of Lab 3, it's actually not as difficult as an exercise as you may think. You already get a hint of how you can implement the additional neighbor interaction from looking at this constraint. So hopefully this will be pretty straightforward. So finally, at the end of this lab, there is a bonus exercise. Now, the bonus exercise will not be graded, but for those who have completed all the exercises above, this should be fun to try on a real device. Here you will get to explore error mitigation to see if this can further reduce the effect of errors to give you better results. So that's all with regards to Lab 3. Lastly, I would like to acknowledge the main contributors of this lab. This lab was created together with my colleague, Kifumi Numata. And we also had many help from our colleagues at IBM Quantum. And I would like to give a special shout out to Yukio Kawashima, Toshinari Itoko, Kevin Son, and Jennifer Glick, who all provided very helpful feedback while we were developing this lab. With that, I hope you all enjoy working on this lab as much as we've enjoyed creating them. Feel free to post questions in the Discord channel. Good luck, and I hope to see you again soon. Thank you.